My name is Lon Lei, and in this session, I will be discussing our work towards net zero carbon within the Amazon fulfillment network. This freight train carries approximately 100 tons of cargo per car, and there are roughly 100 cars in a typical train. This is 10,000 tons. Now let's compare that to the amount of work that is performed inside an Amazon fulfillment center. We definitely move a lot of goods, as you can see here. So during peak, a typical Amazon Robotics sortable facility conveys about 500 tons of goods per day. This is only 5% of what that freight train carries at once. So why is it that the total power of electric motors in a fulfillment center equal to the power of that train? This is one of the main questions that I will be addressing in this session. And in this talk, I will show the implications of this large discrepancy to the entire building's power distribution infrastructure. And finally, I will discuss technology solutions that will solve this discrepancy and will enable Amazon to get closer to achieving our net zero carbon pledge by 2040. This here is a schematic of the power distribution infrastructure from the source outside of the building to consumers such as HVAC, lighting, charging stations, and automation equipment. This session will focus on automation inside of the building, but it will tie it all together at the end for implications at the building level and beyond. Now, automation in the Amazon context consists of traditional material handling equipment, structured fields for drive units, robotic arms, matrix sortation architectures, and autonomous vehicles. So let's first talk about traditional material handling equipment, such as conveyors, which are transporting the majority of goods across our fulfillment network. Now, the basic building blocks of the conveyor consist of pulleys, which are known since ancient Egyptian times, gears whose earliest use dated back to 400 BC in China, the electric motor, which has been around for almost 2 centuries, and the conveyor, which is more than a century old. So why are facilities as modern as Amazon robotic sortable sites still populated with this technology? What do we call this technology if not modern? I would call it proven. It is so proven that even today, this technology is still conveying the majority of goods across our global fulfillment network. So why don't we just keep going, right? Because this technology has reached its theoretical limit in efficiency and is no longer able to meet the needs of our modern times. At Amazon, we've pledged to reach net zero carbon by 2040. This will require innovative solutions with contributions across many sectors of Amazon. So now let's decompose the typical Amazon conveyor drivetrain into its components to understand why the proven technology is not compatible with our net zero carbon goals. Each element of the powertrain is not 100% efficient to begin with. So for example, the electronic driver, also known as VFD, is at best 89% efficient. The existing induction motor efficiency has reached a theoretical limit of 87%, And the worm gears that adjust the torque and speed ratio are at best 76% efficient. And finally, pulleys are at best 94% efficient. So now if we multiply the efficiency of each component together, we get at best a system efficiency of only 55%. Now let's dive deeper and examine the efficiency characteristics of the components as a function of load. So our systems are designed to handle peak loads, and for us at Amazon, that's the month of December. A key concept to note is that efficiency varies as a function of load for each component of the drivetrain. So for the majority of the year, which we call off-peak, our conveyors are only handling loads ranging from 10 to 30% of the peak load, shown here in the gray zone. So now, once again, we do the math, we multiply those efficiencies together, and it tells us that we will be way below 55%, which is why it's so bad from an efficiency standpoint. Now, to make the problem worse, each engineer who designs the components of the drivetrain habitually adds a safety margin to their design, leading to over-design factors of up to 6 times the peak design needs. So this could push the operating conditions to this very steep drop-off zone in efficiency, thus amplifying the losses significantly. So now let's take a tour inside an Amazon robotics sortable facility where we collected data on the power consumption of every single motor drive on every conveyor through peak, which is the month of December. This is the first comprehensive study of power consumption by automation equipment inside an Amazon facility. This figure here shows energy consumption by all motors recorded at the main distribution panel from October 31st to January 15th, and that's shown in the blue trace. And for comparison, we show here the pink trace, which is the daily weight of packages that were conveyed through the facility during the same period. So as you can see, there is a qualitative agreement between the two traces, meaning the energy tracks the weight, and both are fluctuating as demand changes throughout the year. Quantitatively, however, there are key differences. So during peak, the daily outbound weight on average increased from off-peak by 51%, whereas energy consumption increased by only 5.1%. So what does this tell us? Right. First, the majority of the energy is spent moving relatively empty conveyors. And second, the drives that populate our warehouses are too large for the loads that they convey. So tying this back to the key characteristics of electrical mechanical systems losses discussed earlier, oversizing is just really bad from a system efficiency standpoint. This data set confirms that oversizing is a systemic issue across the entire fulfillment center. So now let's dive deeper and take a look at the energy consumption of an individual conveyor drivetrain, which is sampled once every 3 seconds, shown here in the blue trace. This data enables us to glean a wealth of information about conveyor operation, such as these 30-minute windows when associates go on break and conveyors are running empty. There's really no reason for conveyors to run empty, right? They really should be shut off instead of wasting energy. So let's zoom in further on one of these transition spots between break and operation. So here, here's where the conveyor is running empty, and here is where there's a loaded conveyor. And as you can see, the power depends on how many boxes are on the conveyor at any given moment. This is the fluctuation in power demand based on load. So there are two key messages that we can take away from here. The first is that the majority of the power, which is 0.84 kilowatts, or roughly 2/3, is spent moving empty conveyor, while only 1/3 is spent moving goods. Second, the drives to perform this job are highly oversized. This conveyor is driven by a motor that is rated to produce 7.5 kilowatts of mechanical output power. But even at its peak, it consumes less than 2.5 kilowatts of electrical power. So if we account for efficiency in converting electrical to mechanical power, this motor is operating only at 15% of its nominal load in that very steep drop-off zone of efficiency versus load curve shown earlier. So what can we do about it? Now this presents an opportunity to evaluate new technology solutions such as mechatronic drives. And what is mechatronics? Mechatronics is an integrated solution of mechanical, electrical, electronics, and firmware in motion applications. Now, recent advances in motor, gearing, and high-power semiconductor transistor technology have led to the emergence of a new paradigm where the performance of an integrated solution is better than the sum of its individual components. So let's take a look at the benefits of this technology. In mechatronics, the motor electronic driver, the VFD, is tailored and programmed to match its control parameters to the parameters of the motor. So this enables much more efficient operation than it's currently achieved by universal third-party VFDs that have to work across a wide range of motors from different vendors. And what about the motor itself? As I mentioned before, induction motor technology has reached its theoretical limit in efficiency. The development of permanent magnet motor technologies offers more than 20% reduction in losses compared to the most inefficient induction motors. More importantly, the efficiency doesn't degrade much at partial loads. Now, what about the gears? With advanced machining capabilities, the gearing industry has produced very high efficiency gears with efficiencies as high as 98%. More importantly, the efficiency doesn't drop much with load as worm gears do. And finally, using the hollow shaft configuration, they can be mounted directly on the shaft of the conveyor, eliminating the need for pulleys in the final fitting to the specific conveyor geometry. So in summary, the mechatronic drive solution presents an attractive opportunity to shepherd conveyor technology into modern times. Now, what does it look like if we combine all the advantages of modern-day components in an integrated mechatronics package? We will not only achieve higher efficiency at nominal load, but we will also flatten the load curve. As this slide shows, the green curve represents the efficiency of a permanent magnet motor, while the yellow curve represents the efficiency of an induction motor. So furthermore, if we proper size, we will shift the operating conditions to the right towards higher efficiencies. Now let's do a recap of what I've covered thus far. First, the current conveyor drive technology is inefficient and oversized. The second is that progress in mechatronics field has produced a technology that can solve our problems of inefficiency and oversizing. So how do we quantify this impact? So in this work, we developed an algorithm to model energy consumption of advanced solutions using the VFD data that we collected for every single motor drive. And for the first time in the industry, we have developed a model that takes into account partial loads and efficiency of every component in the drivetrain. Shown on the left is a schematic of the algorithm that we apply to model every motor drive. So by applying this procedure, we calculated the largest value of torque that the drivetrain needs to generate and use this value to identify properly sized mechatronic drives for each conveyor. From new component efficiency data, we calculated total efficiency of the mechatronic solutions. And finally, by integrating the power over time, we obtained energy consumption of the proposed solution. And using this model, we analyzed the impact of replacing every motor drive in the facility with properly sized mechatronic drives. We found that by doing so would result in 42% energy savings and carbon footprint reduction, which is equivalent to 820 metric tons per year of carbon footprint reduction per site. Now, this is the largest entitlement for reduction of indirect emissions within the building. Now, what about the cost of this technology? Well, it comes at a higher price, but due to the reduction in power consumption, it enables us to reduce the size of the power distribution equipment, which in fact leads to a net CapEx savings. And additionally, we'll be seeing net OpEx savings from utility bill savings. So based on this analysis, we have launched several pilots in Europe and in North America with initial results confirming energy savings as predicted by the model. In Q2 of this year, Amazon in Europe has mandated that all new builds be equipped with mechatronic drives. In North America, we're working with machine vendors and design partners to build this into standards moving forward. Okay, so now I'm going to switch gears away from traditional conveyors to discuss other opportunities for achieving net zero carbon in the automation realm. This here is the Amazon item singulation machine. It's an advanced technology system that takes a tote filled with items and singulates them. When we were preparing for deployment of this machine to Amazon buildings for the first time, there was a concern that additional electrical service will need to be added to the buildings to meet these new demands. So in doing a deep dive into the electrical ratings of this machine, we actually realized that the nameplate rating, which was 60 amps, was significantly larger than the actual machine demand. And this is actually due to the common practice of machine integrators to add up all the power-consuming elements of the system, assuming simultaneous maximum current draw. Now, in reality, the probability of this event occurring is next to zero. The machines and systems inside our facilities operate according to flow logic with motion profiles that don't follow the model of simultaneous maximum current draw. So what do? We modeled the flow of goods through this machine and performed measurements to verify the model. The machine originally, as I said, had a nameplate rating of 60 amps. And as you can see here, it consumed in total no more than 3.5 amps, which is a factor of almost 20 times discrepancy between nameplate rating and actual demand. So rating to actual demand carries two benefits. First, it will result in utility cost savings because we will not be penalized for consuming less power than design capacity. And second, it's going to be more sustainable as we won't be building oversized power distribution equipment and infrastructure. Now, this case study performed on this particular machine has led to a broader strategy in Amazon Robotics of proper rating of all automation equipment during the development phase of systems. And we also performed the first comprehensive measurement of all automation equipment inside our facilities, not just conveyors. So measuring demand through peak, we found maximum utilization of design capacity of 45% by any given automation equipment. For the full building, there is an average oversizing by a factor of 5x. So this data shows that there are clear opportunities to ensure proper rating of and sizing of automation equipment across the board. Now, in robotics, we are continuing to innovate and develop new automation architectures to keep up with demands of our growing customer base and shorter delivery times. Therefore, the composition of automation equipment is expected to change. The sortation that has been performed by traditional conveyors may shift towards more advanced and integrated robotics solutions. So we're performing energy studies at the systems level, introducing energy efficiency as a key performance indicator for evaluating systems design and trade-offs. Shown here is a new robotic sortation solution with sortation performed by a fleet of drive units or robots that we call Pegasus. An area of opportunity here is to leverage artificial intelligence to perform path planning and traffic routing for optimization of power consumption. Another area of opportunity for optimization of power consumption is to study the time dynamics of robotic systems. When you have tens or hundreds of robots that operate independently in the facility, there is a probability of all arms demanding maximum power at once, as shown on the left animation. Therefore, in this scenario, the building's power distribution infrastructure should be designed to accommodate this maximum power demand. However, we can envision that using AI, we can control the motion of the robotic fleet by phase synchronization to avoid the overlap of their maximum power draw. This will lead to the immediate benefit of a downsized electrical capacity requirement, and it will also enable optimization of power consumption along with other key performance indicators such as throughput. Okay, so just to recap, we discussed opportunities in the automation realm from new motor technology to AI for optimization of robotic systems. This has implications for the rest of the building. First, making automation more efficient means we're dissipating less heat, and so our air conditioning systems will work less. The transformers will be smaller, and for existing buildings that are oversized, reduction of current draw in existing infrastructure will result in lower resistive losses, which leads to an overall net benefit in power consumption. So it means we'll be drawing less from the power grid. And here, I would like to focus your attention on the grid. So currently, we are using AC power supply. However, the consumers of electrical power in the building are intrinsically DC, so this means that there's a conversion involved in the scheme. At the same time, we're adding alternative energy sources to our buildings, such as solar, which is intrinsically DC, but we're converting to AC and then feeding this back into the grid. Now, this AC to DC conversion stages are adding losses, and they appear unnecessary from an energy efficiency standpoint. So let's look at how we can benefit from going directly to DC distribution within the building. Now, DC has several advantages over AC. First, the current carrying capacity of the same gauge wires is higher for DC. And second, there are no power factor losses. And third, there are no rectification stages, so we don't need transformers. And these advantages are estimated to provide 8 to 10% across the board energy savings. And moreover, the DC power distribution approach is synergistic with the rapidly expanding electrical vehicle and other DC charging infrastructure that we're building. So to sum it all up, in this study, we discovered a systemic issue of oversizing that affects drivetrain, power delivery infrastructure, and power rating of the equipment that we deploy and operate. Now, proper sizing alone would dramatically reduce energy consumption, operating costs, and capital expenses, and it will have an overall positive impact on the carbon footprint reduction. And then we discuss with emerging technologies that have demonstrated their potential in more energy efficient operation, and these should be implemented across the entire fulfillment network. And the architecture of the conveyance network and its control algorithm should take into account power efficiency as a key performance indicator. And I'm sure that the experts in artificial intelligence in this audience have a tool set that can further improve this efficiency. So I believe the future is bright. We have large levers to reach net zero carbon, so we don't need a large freight train engine to convey the goods in our building. Thank you.